Hi everyone, my name is Ayman Boustati and I'm presenting our work on amortized variance reduction for doubly stochastic objectives. This work is in collaboration with Sattar, James and team. Doubly stochastic objectives take the form of a finite sum over expectation terms. This type of objectives can be estimated without bias by subsampling the finite sum and evaluating the expectation with Monte Carlo sampling. Monte Carlo sampling can be done by generating a base randomness epsilon in this case and evaluating the individual expectations with Monte Carlo averages. Subsampling can be done by choosing a mini batch over all the sum elements, summing over that mini batch, and scaling accordingly. This type of objectives is very prevalent in variation inference literature, such as black box VI, deep Gaussian processes, and variation autoencoders. By their nature, doubly stochastic objectives induce high gradient variance. This affects the optimization. In this work, we aim at dynamically reducing the Monte Carlo variance throughout the optimization with control variates. Our main observation is that different mini batches produce different distributional behavior in the gradient. This is illustrated with the figure on the right. We start off with the Gaussian base randomness epsilon. For two different mini batches, we plot the gradient as a function of epsilon. We can see that different gradient behavior as a function of epsilon. This induces different distributional behavior, as can be seen from the histograms on the right. We have a skewed distribution for the orange gradient and a symmetric distribution for the blue gradient. Using a linear control variate, we can reduce the variance of the gradients by computing a control variate coefficient over the entire dataset. This is able to reduce the variance of the orange gradient, however, it inflates the variance of the blue gradient. Instead, we propose to use a context-aware control variate coefficient that takes into account the mini batch elements. Hence, we will have a different coefficient for the orange gradient and the blue gradient, which in turn is able to reduce both the variances of the orange and the blue. Our idea is summarized as follows. We propose to control each mini batch element separately. Hence, we have a control variate coefficient for each point in the dataset. This is C in this equation. This, of course, is very prohibitive for large datasets in terms of both storage and computation. Consequently, we propose to amortize the control variate computation with a recognition network, which is parameterized by phi. The individual gradients are then aggregated over the entire mini batch, for example, by simple sum. And to learn the parameters of the recognition network, we minimize the variance of the control gradient with respect to these parameters. This can be done throughout the optimization by interleaving a gradient step on the variance objective with a gradient step on the original objective function. In the paper, we derive two objective functions for the variance of the gradient. The first one is expensive but has a lower variance. The second one is cheap but has a high variance. In the paper, we have a third one, which is also cheap with a higher variance. To verify the variance reduction throughout the optimization, we take a snapshot of the gradient variances after 250 iterations, 500 iterations, and 1,000 iterations. We can see that the amortized control variates in orange are able to achieve higher variance reduction than the context-free one in blue. And this can be seen on both a logistic regression example as well as a deep Gaussian process example. Finally, to test the effect this has on optimization, we plot difference in the negative elbow traces of the optimization with the controlled gradients from the optimization with uncontrolled gradients. We see that amortized control variates have better performance during the optimization than the context-free case. For more information, please check out our paper or contact me directly on email or visit my website. And thank you very much for listening.